k uh, pairs of cities that you have to travel between. So basically, like suppose say let's consider let's understand this with an example. Like the first case is 2 1 2 1. What is this? 3 4 6 5 3 6 5 6 and 5. So this is the graph, original graph we were given, and the weights are 5, 7, 4, 8, 2, 4, 8, 2. So these are the weights that are given, and basically, what we are given, what we have asked to do is that so the pairs of cities are 1 6 and 5 3. So first we have to find the minimum path length from 1 to 6, and then we have to find the minimum path length from 5 to 3. But the catch here is that you don't need to find the minimum path across the graph, because that would be very easy. What you're allowed to do is like you can change one edge weight to 0. Like suppose if I want, I can change this 4 to 0. I can make it 0. So that is the problem, that you can change one edge to 0, and you are given like pairs of vertices between which you have to find the shortest path, and you have to minimize the sum of the shortest paths between those pairs of vertices. So in this you can choose either of these roads, 2 4 and 4 6, and make them 0, and that would give the total path cost for 1 to 6 plus 5 to 3 divided to 22. So that is the answer for this, and is the problem. And the constraints are n is less than equal to 1000, m is also less than equal to 1000, and k is also less than equal to 1000. K is the number of pairs of vertices that you given. Like so, the constraints seem like that some n square type, n square log n type something, nm log n, something like that might work. Yeah. So that is the problem, and I'll give you guys 5 minutes to try this yourself, and if you have any ideas, you can share.
A few minutes later.
Any like starting ideas, like some brute force approaches.
Well, I would imagine like the first idea that comes to my mind is like find how many times each edge is sort of being counted, and then like calculate if we make each of them zero, like how much time, how much cost reduction that would
Yeah,
represent, and then choose the best one.
yeah. So definitely, like that is a good idea. So like what Vijay is saying is that uh, basically, so like in suppose in this path 1 to 6. So like if you consider, like if you're considering to make this edge 0, then how like what effect would it have on the pair, like the k paths that you have to sum of, that you have to find the sum for. So like if you are choosing 2 4, then it comes in 1 to 6, and it comes in the other thing was 5 to 3, and it comes in 5 to 3 as well. So like suppose, so basically what you can do is like having like without this condition of removing like making any edge to 0, you start off with finding like shortest paths between or like all the k pairs that you're given, and then you see like is 2 4 being considered in how many of those, and how would it change that. So that is a good starting point. Like the approach is like it can be built on this. Like so firstly I would like to point out that the brute force approach is that you can just like for each, you can iterate on each edge, and like you try to make it 0, and then for each edge you run a Dijkstra from like every other node, that would be what? Mn log n. That would be Mn log n. And this is over all nodes, all edges. And plus, after the like running a Dijkstra, you need to like find the sum of the shortest paths for each of the things. So that would be a plus k additional. So that this is the complexity that you get like by naively brute forcing. But like this is fine, but this is not fine. Like m square and log n would TLE. So you need to optimize this somehow. Like you don't need to recompute the extra every time. Like if you are smart enough with the computation, you will realize that you don't need to run the extra every time because you're just changing the node between one edge senses that you need to think of. Bridges, like here the graph is not guaranteed to be a tree or something like and it's given that it's like connected. I think yeah, it's given that it's connected. So I don't think like changing the weight to 0 won't change the connectivity. So oh, like are you talking like that bridges definitely need to be there in the parts or something like that? Oh, yeah, maybe we can try that as well. Yeah, so I think the issue that you'll run into is like for so like in this case as well, if suppose I gave you 5, 6, and 3, 1, then these parts like don't have anything in common. So then you'll have to make like a trade-off between that. Like this is a bridge right now, but if I give you 5, 6, and 3, 1, then this is in neither of the paths. So yeah, so bridge doesn't need to always be in the path. Yeah. But yes, like all of these ideas are on in the right direction. Like you need to figure out basically how does the path length change if you like change just a single inch. How does the pairwise distances change? So you're saying can we like this for each edge how many paths it contributes to and take max? Okay. So you were saying that you like want to do it greedily, like for each edge, you want to check in how many paths it's coming and like multiply it by the cost you're reducing the sum to. And yes, doing something like that. I think yeah, that will also work well. But like you'll have to think about how you'll check that if a edge is like in included in that path, something like that. Like I think yeah, this is a uh, I think this is fine. Like you can probably continue in this direction. This might this might be a little more tedious to code, but I think this approach is also fine. So I think now I'll discuss the approach because someone has like found a correct approach. So I'll discuss the less tedious approach. So basically, if you notice, then let's consider two vertices like A comma B. And suppose the edge you're changing is like X comma Y. So how does the distance between this A comma B change with respect to X comma Y? So like if you think about it, there are two cases. Either X comma Y was the edge XY was originally in AB or it wasn't in AB. If it wasn't in AB, then the distance remains AB. But if it was in AB, then what happens is that the shortest path length between A to B is either this, like only these two things are possible, plus uh, YB, or this AY plus xy plus xb. Like because x comma y is contained, so either it could be like you go from a to x, then x to y, then y to b, or it could be like you go from a to y, then y to x, and then x to b. Like only one of these two things can be the case. And if you notice this, so basically you can always like so a path length that was already there without even like making any edge zero, that you can anyways always guarantee. Like so this is always the an option. Like you can always travel between A and B in this much. And if it was traveling through x and y, then you can also make x comma y zero. And so you can do either this or this, like the minimum of these two, either this or this. So after removing the edge xy, the distance becomes the minimum of AB, which was like the original distance. This AX plus BY, I'll say these terms as 1, 2, and 3, 4, because I don't want to write them again and again. So 1, 2, and or 3, 4. So the distance between A comma B in the new graph is the minimum of these three for a particular edge. Note that if you're changing x comma y, this won't change because you are going from x to y later on. Why would you have gone from x to y before as well? Like that would not make sense because like you want to minimize the path length. So xy won't be here, so this won't change. This would be like the same as the original graph. This would also be the same as the original graph again by the same argument, and these two also will be the same as the original graph. So you already have these pre-computed. Like so, what you can do is basically just run a Dijkstra in the start from every node and pre-compute the distances before like making an edge zero. And after you make an edge zero for each of the k roots, this is like the new value. So the minimum of the original value only before making an edge zero, or if you make the edge x comma y zero, the minimum of these two values you also have as an option. And so like you can iterate over all edges and try to minimize the sum uh, in this way. And this the time complexity of this if we analyze, so this would be what? You're iterating over all edges. You have like a pre-computation of the Dijkstra in the start. So you're doing a Dijkstra from every node. So that is mn log n plus your for each edge you're like just considering this sum kind of, and this sum is like O of 1 to compute because you already have this a comma b, this one term and two term, three, four, all of these are computed already. So this is like O of 1 and you are summing for all the k roots. So total k iterations you need to do. And so this will be mn log n plus m into k, and this is like this will fit in the constraints. Is there any doubt in this approach? Otherwise, I can show you the graph. So, I think I'll show it on here for you. Yeah. So I think, yeah. So the code is like this only. Like I first coded extra, and after that, it's just this is like so. This is like pre-computation, and then yeah, it's just you iterate on all edges and try to minimize the sum. As I mentioned, like from uh, that node to x, then from the second node to y, or from the first node to y and the second node to x, or the original distance itself. And yeah. So if anyone has any doubts in this approach, I think Harshit's approach would also work Like you can also do that, but yeah, you will just have to like it. I think will be a bit tedious to code. Like you'll have to check for each edge, like which all paths that is it coming in. Like you'll need the explicit path as well for each of the K pairs. But I think yeah, that is also easy to you can backtrack. Yeah. If there are no doubts, we can go on to the next problem. I'll give you guys 2 minutes to ask anything. Oh, okay. So, okay, I'll explain it again. So basically, like, suppose you have like two. So suppose A comma B is part of the K roots, right? So while you so the algorithm is that only, right, that you iterate on every edge and you try to make it zero and then update the distances for all the K roots. So suppose you are trying to make this edge zero. This is x comma y. So there are two cases. Either this x comma y was a part of the original shortest path without like changing anything, or this x comma y wasn't a part of the original shortest path. So if the x comma y wasn't a part of the original shortest path, then if it's not a part of the new shortest path also, then the distance remains a comma b, and this you can achieve anyways. Like the edges you were taking earlier, you can still take them and their weights haven't changed. So if it was not a part of the original shortest path, this you can always make this shortest path. Like that path you can always take. If like it was a part of the original shortest path, then the distances will change. Like then the path length would change. So if it was a part of the original shortest path, so its path value will now decrease. So what will it decrease to? There were it could either be that if x comma y is a part of the path from A to B, so it could either be that you are going from A to X, then you're going from X to Y, and then you're going from Y to B, or it could be that you are going from A to Y, and then you're going from Y to X, and then you're going from X to B. Like only these two cases are possible. In this case, this now becomes zero. So it's only this distance A to X and this distance B to Y. So you can do it in this much distance as well. And in this case, this becomes zero. So it's from A to Y plus B to X. So it's the minimum of these three things. The final distance can only be one of these three. And like you can always achieve all of these three. That is the claim. And the answer should like the distance should also be in one of these three, and you can achieve all of these three. So what the final distance would be just the minimum of these. Like whatever is the least amongst them, that will be the final updated distance. That is the idea. So and these distances are like from the original graph only. So this is like already pre-computed. So this is all of this is over one to compute.
Also, in Harshit's approach, like contributing like how many times a path, an edge is in a path,
Mm.
wouldn't that be like sort of greedy? Because after like making a thing to be zero, like it could contribute to more paths as well.
Yeah, like that was also something like even crossed my mind. So we'll have to look into that as well. I think, uh, yeah, the issue there is that it might happen that after you make an edge zero, the paths between some vertices like might change. Like now, maybe you are trying to take that edge and take a path because its weight is low. So I think I think we can construct a counter example for that. Uh, so basically, suppose this was like 2, 2, 2, and this was like a very high thing. So yeah, so now from let's say you don't have this edge, let's suppose, and you have this instead. Hmm. So this is 4. So yeah, so what can happen is that if you try to make this 0, then earlier this 1, 4 was not a part of the path from 2 to 4, but now it becomes a part of the path. So yeah, so this will I think fail. Yeah, because like now this 1, 4 is contributing more. Like it's not just reducing the distance between 1 and 4. Like earlier, this edge was only being used in the distance between. It wasn't being used at all. Like this edge wasn't being used at all because there are other ways to travel between vertices. But now, if you make this 0, then this edge will be used between different parts. So yeah, so that is an issue in that approach. That is greedy and it won't work.
Yeah, we can even directly take this 4 and 1 as well.
Yeah, yeah. Yeah. So I think the approach is clear, hopefully.
Yeah. So we are discussing this question. In this question, we are given a connected undirected graph with consisting of n vertices and m edges, and it is given that there are no self loops or multiple edges in the graph, and we have to direct its edges in such a way that the obtained directed graph does not contain any paths of length 2 or greater. Let me basically the we have to direct the edges in such a way that any path length is not greater than equals to 2. Therefore, say it is we direct it edge from 6 to 1, then we cannot direct any edge from 1 to any of the remaining vertices, because in that case path length will be greater than equals to 2. So yeah, you have 5 minutes to think of the question. If you have any ideas, please suggest. Yes, your idea is completely correct. We can think of it with the help of bipartite graphs. Just this, please. This was the sample test case.
I'm not sure, but like just start from any node and like do a BFS and just color the other levels in one. I mean, in the different colors. I mean, put them in different parts of the bipartite graph. Does that work?
Yes, your idea is completely correct. We can simply run a simple BFS or DFS and can color the nodes alternatively. And for each node, say we have decided two colors, 1 and 0. So we can denote either of them to be a sink or a source. So in that way, we will not have a path length greater than or equals to 2 in any case. So the main idea of this problem is that we need to uh, we need to construct a directed graph out of it, so that every node is either a sink or a source. What is a sink? A sink is a node such that all edges are directed into this node, and a source is a node such that all edges are directed out of this node. So if we are given a sample graph like this, and we are given that there is not any node k such that one edge is directed into the node and the other edge is directed out of the node, which means every node is either a sink or a source. And also, sinks and sources are can only be placed alternatively. There cannot be two consecutive sinks or source. For example, node 1 and 2 are connected with each other. Then either one is sink or two is sink. It is not possible that both of these nodes are sinks. So basically, we want to divide these nodes into two sets such that one of the sets is a set of sinks and the other is source. And this is directly related to bipartite graph. What is a bipartite graph? It is a graph such that we can partition into two sides. For example, I will partition this graph into two sides, 1, 3, 4, 2, and 6. Yeah, so in a bipartite graph, we can partition it into two sides such that edge only crosses from one side to the other. Therefore, in such a way, we can color the nodes alternatively. And also in bipartite graph, there is a strict condition that there are no odd cycles in the graph. Because if there is an odd cycle, say 1, 2, 3, then we cannot partition it into two sides such that edges only crosses the partition. And this is an if and only if condition. So if the graph doesn't have an odd cycle, then it is a bipartite graph. And if it has an odd cycle, then it is not a bipartite graph. So in this question, if the graph has an odd length cycle, so the answer is simply no. And if the graph doesn't have an odd length cycle, then we can simply run a simple BFS or a DFS to partition to color the edges alternatively. Say we give coloring 1 to the left side and 0 to the right side, and we simply denote 1 by sources and 0 by sinks. So our edges will be directed like this. And this is a sample test case. The edges were given as 1, 5, 2, 1, 1, 4, 3, 1, 6, 1. And we had to output 1 if edge was directed from the first node to the second node, or 0 if it was the other way around. So for our output in this case would be 1, 0, 1, 0, 0, which matches our output for the sample test case. Does anyone have any doubt in this question, or else I will show you my implementation for this question? You have 2-3 minutes to think of this solution, and you can point out any doubt if you have. Yeah, sure. Yeah. So in a bipartite graph, a graph is bipartite if and only if it has an odd cycle. And why is this true? Because Say if we have an odd cycle 1, 2, 3, 4, 5, then we cannot color the edges alternatively, because if we start from one vertex, say 1, and color it 1, then we will color its adjacent vertices at 0, and then its adjacent vertices as 1. Then our last uh, two consecutive nodes will have the same color. And therefore, if the graph has an odd cycle, it is not bipartite. And if it doesn't have an odd cycle, then I think we can simply partition it into two sides. Say say our cycle was 1, 2, 3, 4. So every cycle can be partitioned in a way that it just goes from 1 to 2 and 4, and from 2 and 4 it just goes to 3. So yeah, this is a necessary condition for a bipartite graph. I hope it is clear to everyone. Yeah. Yeah, if you don't have any doubt, then I will show you my implementation. The constraints were that number of vertices and edges are till 2e5, and thus a simple DFS or BFS would work easily. And yeah, so just I first took the input as an agency matrix and then run the DFS. In the DFS, I am passing color as an argument, and I'm maintaining a vector of length n, denoting the color of each node that I have visited till now. If the color, if I am visiting that node again due to a cycle, and the color matches our previous given color, then we can continue running the DFS, and the answer is 1. Basically, it doesn't have an odd cycle. And if it doesn't matches our previously denoted color, then we will return 0. And basically for each node, we will run the DFS again for its successors with the node itself as the parent. And we will have to denote the color 1 minus color, basically is the opposite color to the next nodes. And we will just return the AND of all the DFS operations, because if in any paths we have a color mismatching, then our answer is 0. So yeah, if the answer is 0, then we simply return no. And if the answer is yes, then we have coloring in our coloring matrix, and we will simply return 1 and 0 with respect to our output vector. And you can try implementing this yourself and you will understand it more clearly. Any doubt in the implementation of the question? Yeah, if it's fine, then we can move on to the next question.
The goal is to find the number of strongly connected components present in this graph. So if anyone has any ideas how we can do this, let me know. So in a directed graph, you want to find the number of components such that you can go from every vertex to every other vertex within that component. Any ideas? No. Okay. But I mean, so in suppose you had an undirected graph, then this would be simple, right? What would you do in an undirected graph? Anyone? If it was undirected and you want to find the number of component such that you can get from every single one to every other one. Uh, yeah, these joints, why? You can simply do DFS, right? Yeah, exactly. Yeah, simple DFS or BFS, anything would work. Yeah, but here, of course, that's not the case because you need to check connectivity both ways. A path from U to V does not imply a path from V to U. So here you would have to do something a little bit different, but the idea is kind of the same. So I'll start with this example only. So this was the example given in the problem. And this is a graph, and you want to find the number of strongly connected components. So just by looking at it, can you tell how many components are there such that you can go from one vertex to every other vertex and back? Anyone? Like, this is a small example, you can directly see and tell. Yeah, you're right. So these two, because this contain the first one is a cycle 1, 2, 3, so you can go from every vertex to every other, and 4, 5 as well. You can go from 4 to 5 and 5 to 4, but within these strongly connected components, you can't communicate because um, you can't go from the 5, 4 component to the 1, 2, 3 component. So now we need an algorithm to find these. The first step would be to start DFS at any arbitrary node, like run a normal run of the DFS on the whole graph. And then the important thing is to store the order in which each node gets fully explored. So you can say start with 5, then go to 4. And now you don't have anywhere else to go from 4 because 5 has already been visited and you can't go to 3. So you mark 4 fully explored and then you store 4. Then you visit 5. Next, suppose you visit 2. Doesn't really matter. And if from 2 you can go to 3, 3 to 1. And now again, you are out of options. So you mark 1 as fully explored, then 3, and then 2. Now the next part is interesting. And it starts with an observation that the connected components in this graph, as well as if I reverse each edge, then the connected components would still remain the same. If I can't go from, it's just that the direction would reverse. So, like earlier, you could not go from the 1, 2, 3, could not go from the 4, 5 component to the 1, 2, 3, but now you can't go from 1, 2, 3 to 4, 5. But there's still the strongly connected components themselves remain exactly the same, they remain preserved. Okay. And also a mathematical kind of guarantee in this. Yeah, a guarantee in this is that if you visit one connected component, if there's a path from one connected component to the other, so for example, there's a path from this connected component to this connected component, like this, uh, then then you would fully explore this for exploring this. Uh, and this would always be the case no matter where you start the DFS from. And you can prove this, but I'm not going to go over it. So I'll state the claim again and you can prove it yourself. It is that whenever if there is a path from one connected component to the other, but they are not the same, they do not belong to the same connected component, then you would first fully explore the second connected component before you fully explore the first one. Okay, so how this helps is that when you reverse the graphs, when you reverse all of the edges, you know that you can start um, from the reverse order of what you visited in the first run. So you visited the nodes in this order in the first run. If you reverse this order, then you know that if there is a path from, say, A to B, but not B to A, then you would encounter some element from A before you encounter some element from B in the reverse ordering, right? Because of the previous claim. The previous claim said that you would fully explore A after you fully explore B. So in the reverse order, you would first encounter an element from A before you first encounter an element from B. All right. So now, because of that guarantee, uh, what you have now is that when you start here, if a node is reachable from 2 in this reverse graph currently, then it must belong to the same strongly connected component as 2. So we visit everything that is reachable from 2 and we mark it with the same color or number in the board. But right now I'm using colors. So yeah, this is the same connected component as 2. And next we start with 5 because 3 and 1 have been visited. And yeah, then we get this. And that's the algorithm. I hope it made sense. Do you have any questions? Uh, okay, so I'll just maybe show you the code. Yeah, okay. Yeah, so the reason why it works in the second run is that you can't visit any node from. So because you first encounter um, a node from which there, so like in the previous graph you had A and B, right? So the reason you you could have gone from A to B but not from B to A. So in the reverse graph you can go from B to A but not from A to B. This is why you want to mark all of the connected, like all of the vertices from A first, because if you started your DFS from B, then you can go to A, but it is not in the same connected component. This is why we reverse it, so that you first mark all of the edges, so that you first mark all of the vertices in A before you mark all of the vertices in B, so that it remains true that all of the reachable vertices are in the same connected component. So like if you could maybe think of this in terms of a larger uh, meta graph of such of connected components like this. uh, with an arrow like this. And you want to mark everything in this one first, because if you start a DFS from here, you'll go to this, even though it's not the same connected component. I hope that makes sense. Mm. All right. Here is the code. Uh, we first define a few things. This is like the maximum possible value of n. Then this is the forward graph. This is the reverse graph. This is the order in which we store the elements. So like this list, and this is this is component. So like which component does it belong to? In our case, we marked the components purple and green, but for a computer we need numbers. And this is a visited array for the first one. So in this code, first we take input, and then this is the first run of DFS. And what it does is marks it visited and just simply adds a vertex to the order when you are done fully exploring it, not when you first visit it. So like, yeah, it will first explore all of its neighbors and then go to this. This is just सबसे के -1 कर दो ताकि for this checking. Anyway, you maintain like a number corresponding to each connected component, and start from the reverse, because you want, as I explained, you want to visit the reverse ordering that you did initially. And you do your second kind of DFS run, which marks this, fills this array with numbers corresponding to the connected component of that particular vertex. Yeah, and then just give the output. That's what the code does. Code is pretty simple, but I hope you get the idea. Any questions? Okay, then go to the next problem then.
So I'll explain the problem. Basically, like the problem statement is very weird. Like you can try reading it, but the statement is weird. I'll explain it simply what the problem is. So basically, what you have is that. So basically, the problem is that there is like a city. Like there's a graph that you're given, and uh, you are given the edges in this graph, and the thing is that each edge is not like accessible at any time. Like so basically there are like suppose timestamps assigned to each edge. So suppose like there could be timestamps like this assigned to each edge. Now what is happening is that so you are given an array of timestamps. So like suppose the array was something like this. So at the first instance, only the edges which have the timestamp 1 can be used. No other edges can be used. So at the first, like at t equal to 0, like at time equal to 0, only edges which have this timestamp 1 can be used. So these two edges can be used and these edges are not available to us. You start off at the node 1. So suppose this is node 1 and these are like 1, 2, 3, 4, 5. And your goal is to reach the node n, like the last node, which is 6 in this case. So at t equal to 0, you have no access to uh, nodes which are to edges which are like which have timestamp of the first element of the array. Like so, which have timestamp 1. So only these two edges are there. Then at t equal to 1, you can only use edges to travel that have timestamp 2 because the second element is 2. Then at t equal to 3, you have the choice to use edges which have timestamp 1. So again, you have 1, 2, and 2, 5, and so on. So the task is that you start off with node 1, and initially you're at the first t equal to 0, you write this timestamp. Now you can use roads of this timestamp, and you have to keep taking roads, and you have to ensure that you reach the node 6 in the least possible amount of time. And time means like in the least possible index of this array. Like suppose you can reach 6 till this index, fourth index, then the answer would be t equal 4, like that. So you have to reach 6, and it may be possible that you can never reach 6 because, like in this case, we can see, like suppose this will get a timestamp of 3, then you can never reach 6 because every time to reach 6 you'll need to take this road, and there's no timestamp 3 in this array. So it is possible that you may not be able to reach the end node, and for that you will return -1. Otherwise, you have to return the first time by which you can reach the node 6, like the last node. So that is the problem. And we can maybe take another example, like this is the example that was given in the problem statement. So 1, 2, 3, 4, 5, they have given a line graph. And basically, so the input format is like the first timestamp has these 4 edges. So this has timestamp 1, and then there are edges like 2, 3, and 5, and these have like timestamp 2. Okay. And the array is 2, 1, 2, 1, 2, 1. Okay. So clearly you can see that in this, it shouldn't be like the answer shouldn't be -1, like because it seems that you have sufficient 2s and 1s. So it should always be possible to reach. But like what is the optimal case? So let's try to think. So at the first instance, the timestamp is 2 and you're at 1. You can only travel to 2 through a route which has timestamp 1. So this is not available. So this moment gets skipped. You can't do anything here. So you don't do anything here. Then you go to this. At this instance, timestamp is 1. You jump to 2. So now you're at 2. And now you go to the next time instant. So again, it's 2. Then you see that you can travel to 3 through 2. So let's suppose you jump to 3. So now you're at 3 and now you have 1. Then you see that, okay, you can jump to 4 again. So you jump to 4 and now you're at 4 and the time is now 2. But now you see that you can't jump anymore. So maybe this was like a bit suboptimal because now you need to wait till this one and answer will be now 6 with in this case. But there is a possibility of doing it in 5 ways. In 5, like till here, you can reach the end. And the method like they've uh, given is this, that you move to 2. You move to 2. So the first thing was right that you move to 2. But then instead of moving to 3 instantly, you wait. Like instead of moving, like you can move to 3 also instantly after that. But then instead of moving to 4 instantly, you wait and you directly go to 5 from 3. So you can do it in 5 ways, in 5 seconds. So that is the problem. And it is a bit tricky. So I'll give you guys some more time to think on this. Like it is hard to come up with initial ideas for a problem like this. So you can take your time. If anyone has any doubts in the problem statement, they can tell. I can explain it a bit more. Yeah, yeah. So if you look at the constraints, N and P are both like 2 into 10 power 5, and the number of edges are also like 2 into 10 power 5. So if you notice, maybe something like an n log n approach can work like, because so the idea is that whenever like you see some, so here also you have to find shortest paths. So whenever you see some problem related to shortest paths, the first idea that must come to your mind is, and there are like weights. So you can see that the edges have like certain weights associated with them. But it's not like it's being summed kind of, but yeah, there are certain weights. So whatever the idea that first should come to your mind is that you might need to modify the Dijkstra algorithm a bit. Like you might need to change some things in that algorithm. And so the time complexity maybe you're trying to look at is m log n or something around that. But yeah, like if any one of you has any possible ideas, let's say we store for each node what is the minimum index to reach this number, the smallest element. Yeah, okay. So I think Harshit, you told me the exact idea. Yeah. So what Harshit is saying is that, so suppose like you are at like say a current index, say current node say 2, and you have like certain roads going from this 2. And for each, okay, so let's say we store for each node what is the minimum index to reach this node. What is the minimum index to, okay, we can explain this. Okay. So basically, yeah, so what Harshit is saying that in this problem, what you the path length, what that means is the smallest index in this array by which you can reach that node. So like by that time, if you are able to reach the node, then the path length kind of is that. So you need to minimize that particular index. So let's suppose like you start off with one, and like there are certain roads going from this one. Let's say 2, 3, 4, 5. These are not directed. I just made arrows, but yeah. Now suppose you want to go to 2, like you want to update the distance for 2, then what would that be? So 1 you're already at here. You will try to check. So this, suppose this has timestamp 3. Then you will try to check, because you're already here. You will try to check in this leftover array when is 3 in the latest. Suppose like in the end there was a 3 here. So 3 is first position is this. So you can reach this 2. If you're just looking at this 2, you're not thinking about the further nodes. If you're just looking at this 2, you can reach this 2 latest by this index at which 3 is at. So you can like, now maybe you are like, I think you should be getting the idea that you can maybe relax the edge like edges in this way, that if you have pre-computed the index by which you can reach to a certain node already, then if you want to go to a node which is adjacent to it and which has like a timestamp of k, you need to check in the leftover part of the array. So like suppose you can reach this by an index I. So in the leftover part of the array, like after I plus 1, whenever this timestamp k is coming first, you will take that edge to go here. Like it may be that it's not optimal for other nodes paths. Like it is possible that to reach here, you are not going to be greedy in like every step. But just for reaching this node, this is 100% like the best idea, best thing that you can do. Like go to the first index that is like uh, an index of k, a value of k. Like go to the first timestamp, and then yeah. So maybe you can think of doing that. And can you like modify Dijkstra a bit to like incorporate for this kind of relaxation of the edges? Yeah, like so you can like the correct approach is that you will need to be greedy. So I was like asking some. I wanted to ask someone for a proof or some like basic idea why you would need to be greedy every time as well. Like it's not that hard to spot. But yeah, like the idea is that if you want to go from one, like if you've already pre-computed for one node, yeah, exactly. So if you've already pre-computed for one node, then if you want to go to a node that is adjacent, you will always try to be greedy in the sense that you will always try to go to the first index which has that timestamp k in the array after like this index I. But as Harshit pointed out, it's always better to reach earlier because even if you reach earlier, you can always wait. Like it's never optimal to reach later than a given index because you can always wait at an earlier index and till that later index if it was optimal to go to a later index. So yeah, you always need to be greedy, as Harshit pointed out. And now you can see like so if you think about it, Dijkstra also has a very similar kind of thing going on. Like you always try to uh, do the best for a node in each iteration. So now you can maybe try to relate the two algorithms and try to like finalize an approach for this problem. I like finding okay, so I'm skipped out a few minor details. So like finding an index, I think it should be obvious though. Like finding an index which has like the first index which has value k is not hard. It is like just binary search. You can store all the indexes for a given value because like t is also from 1 to 10 power 5. So for each of the timestamps, you can store which index, which indices it occurs on, and you can sort that indice array and like just binary search for I. Like you can find the element just greater than I. So that is in login, and that should be like it is login, and for each of the nodes it will be in login. So that should be an issue. But how would you modify the Dijkstra algorithm now? Like, can you modify it and maybe like just someone can tell me how to finish this because it's like 90% done. Yeah. So I think it is clear only now. So I'll just explain the whole thing once, like so that it's perfectly clear. So what we can do is that just maintain a distance like you do in Dijkstra. Is everything to infinity except the distance for the first like one. Oh, sorry. Yeah, like 1 or 0 depending on. I think it was supposed to be. Yeah, because like you're already at this timestamp, so yeah, so it is 1. Now, what you can do is like 0. Now, what you can do is like uh, basically whenever you're at a node V and suppose like at a node U and suppose like D of U is already found out, and it is suppose I. Then what you can do is that you check all the nodes which are adjacent to you, such that v comma u is an edge. And suppose v comma u has a timestamp of t or of k. Then what you do is in the array after I, like from I plus 1 to n, to whatever the array length is, I think it's, yeah, to the end, you check where the first index where you can find a k. So like suppose this j is the first index where there is a value k, and this you can do in log n, because I said you can do just do a simple binary search. So if you find this k, then for v would be what? Just the minimum of already computed v and I. And sorry, this j. And this, if you notice, is like very similar to Dijkstra, and you can just use a priority queue and keep on popping out the elements which have the least distance because they will be finalized. And you can relax the edges which are adjacent to that node, which you just popped out from the priority queue. So I think, I hope this is fine. And if it is, I'll give you 3-4 minutes to think about it. And like if any doubts you can ask. And otherwise we'll proceed to the implementation. What? From first, like from this. Oh, okay. So like okay. So you want me to explain the solution, right? Again, the solution. Okay. So what we the approach is that you store a distance vector, which will be like a priority queue, like the distances you store in a priority queue as you do in a Dijkstra. You so initially distance of the node 1 is 0 and the distance for all other nodes is infinity, same like Dijkstra. And what you do is you pop out the least distance vertex because like that vertex will be finalized. And for each of the neighbors of this vertex, you check, like suppose v is a neighbor of u, you check the edge v comma u, suppose it has a timestamp of k. Now what you do is, so the already computed minimum value to reach u was I. So now till time I, you've already like, traversed the array. So you, the array part that's left is like from I plus 1 to the end. So in this part of the array, what you check is that what is the first index at which this timestamp k is occurring. So suppose like in this part of the array, I plus 1 to the last array, last element, k is occurring for the first at j. So you'll have to definitely wait till j, and it's, as we discussed, it's always optimal to go to like take the path at the index j, because you can always wait later on. So you will have to wait till j and you take the path till take the edge at the index j. And so now the distance for v, what will that be? It will be just the minimum of distance of v that's already computed, comma, you can always reach it at j, because you have reached u till I, and then you can take an edge from u to v at this index j. So this is the minimum that you can achieve. Yeah, and this is like exactly Dijkstra, the algorithm. So you just need to modify the relaxation function. In Dijkstra, you like add the edge weight to the previous computed distance. Here you will need to take this minimum, and the approach is exactly the same. Yeah, and we can move to the code. So the code, as I mentioned, it will be like almost exactly the same as Dijkstra. So you have a distance array, you insert into the priority queue 0 and the source node. And while it's not empty, you find the you pop out the node with the minimum distance, and for each of its neighbor, you find in the remaining part of the array what is the like least index at which. So pos of x denotes the indices which have like a value of x in the timestamp array, and just find the least index which is like greater than the index that we have used up for reaching u. And yeah, like for v, that would be the distance of v would be the minimum of the already computed distance of v and this particular index that we found out from this binary search. And yeah, so if you try to analyze the complexity, this is log n. So you like extra, it is m log n. That part is already there, and this would be like a log n extra. So it's still that one. And yeah, apart from that, yeah, this is simple. So that is the whole thing. So the main idea was that you just needed to think how you would relax the edges, and the approach apart from that is the same as the direct approach. And this is like a very common theme in a lot of questions that there are certain questions where instead of the path length being the sum of edges, it is like the maximum of edges, and still you can do something like this. Like you just need to modify the extra bit, which is what I also pointed out in my lecture. That is why this algorithm is very useful. So if you have any doubts on this approach, you can ask. Timestamp array. Like in the timestamp array, you like iterating over the index of this timestamp array, and you're checking that till that index, whatever edges were available to us in the past. And how are you updating the no? Like, can you repeat the updating thing once? Mhm. So, like, if I am understanding it correctly, you'll at each index of the timestamp array, you need to add and remove edges all the time. Uh, what would be the complexity of that? So, in the worst case, like you might need to alternate. So, suppose like all the edges have like timestamps 1 and 2, and like half of the edges have timestamp 1, half of the edges have timestamp 2, and it's like alternating 2 and 2 and kind of thing. So you need to add edges of 1, and then you need to so acha, you'll be storing all the edges of 2, and you'll be storing all the edges of 1 in a map. Okay. Hmm. Yeah, makes sense.
Will not it give us TLE, because in worst case there are n vertices through which we can visit our new vertex, and we are iterating n times. Basically, at every step we are given the option of whether to choose that edge or not.
Yeah.
So I think it will give a TLE.
Hmm. Oh, okay, you're saying that. Okay. Mhm. Like if you've already used an edge, then you won't be using that edge again. It makes sense. I think, yeah, something like this can work. I think. Like this sounds fine to me right now, but yeah, probably like if when we implement this, maybe we can like figure out what it was. But yeah, I think tentatively right now this seems fine. This approach is good. So, what? Yeah, like if anyone else can point out like if they think they can point out some flaw, they are more than welcome. Like you can type it and say it.
Can you show this question code once? Which
Okay.
question is this?
Yeah. So this is 1887B.
Okay, thank you.
If you have other approaches as well, I think this problem will have a lot of approaches because, like as Vijay pointed out, I think we see another approach and there might be other approaches as well. So if you have another idea, maybe you can share that and we can all think about it.
We are given a connected, undirected, weighted graph without self loops and multiple edges. And we have to basically find weight of the spanning tree containing basically for each edge, we have to find the minimum possible weight of the spanning tree that contains that edge. Let me show you the diagram and I'll explain. Yeah, basically for every edge u comma v, we have to find the minimum possible weight of the spanning tree that contains that edge. Let me explain with the help of the sample test case given. We given Yeah. So we are given this graph in a sample test case, and we have to find out for each edge u comma v the weight of the minimum spanning tree that contains that edge. And the constraints are that number of vertices and edges are till 2e5. So we have to possibly think of a solution in O of n or of n log n type. Any ideas how we can approach this question? I'll give you 5 minutes to think on this question. I hope the question is clear. If you have any doubt in the question itself, you can ask now. Oh, let me see. Find the MST. Yes, this approach is perfectly correct. Basically, we can find the MSG, and for every edge u comma v, which is in the MSG, the answer is simply the weight of that tree. And for every edge u comma v, which is not in that MSG, then we will have to find the largest edge connecting u and v in the original MSG and remove that edge. And we can, yeah, yes, basically do this by using least common ancestor and max weight edge in log n. And this can be implemented using binary lifting. Yes, this approach is perfectly fine. Others also think of this approach. We will talk about the implementation later. First, clear this approach that, first think about this approach that how to find maximum weight edge using LCA. Yeah, we will discuss this later. So I think we can start our discussion. So yeah, Gujrot's idea is correct that basically we will find the MSG of this tree which we can easily do using Kruskal's algorithm that we did earlier. In this case, our MST would be uh, 1, 3 is connected by 1. Then, yeah. So this is our spanning tree for the given graph. And for every edge u comma v, which is contained in this graph, the answer is simply the weight of the spanning tree, which is 8 in this case. But for every edge which is not contained in this graph, let us take an example of the edge 1, 4. So we have to find weight of the minimum spanning tree in which the edge 1, 4 is contained. So we'll simply check the path 1 from 1 to 4 in our original MST and eliminate the biggest edge contained in that path. So, here 3 comma 4 edge is the highest weighted edge in this path, so we'll remove this and our new edge will be 1 to 4. Why is this? Because whenever we'll add a new edge in a spanning tree, there will be exactly one cycle formed, and we will have to remove the second largest edge of that cycle. And the second largest edge of that cycle is the largest edge already initially contained in that path. I hope the idea is clear that what we are trying to do here. Any doubt till now? Yeah. So now the main task is that how to efficiently calculate the largest edge between any two vertices in a tree. Because there are m queries where m is the number of edges, and if we do a normal ON DFS for each query, then it will give TLE as ON comma m will fail to pass. So we have to find an efficient approach to find the maximum edge between any two vertices, and this can be easily done using binary lifting method. We can use binary lifting to calculate basically two things: LCA, which is lowest common ancestor, and we can also use this to calculate maximum between any two vertices. So what is binary lifting? Let me draw a sample tree. Say we have a tree rooted at 1, and the edges are like this: 1, 2, 3, 4, 5, 6, 7, and 8. And we have to process queries of the form v comma h, which tells us that what is the v comma t, which tells us that what is the th ancestor of the vertex v. The naive approach is of complexity O of h, where h is the height of this tree. Because in brute force, we will, in order to simply check what is the th ancestor of 6, I will have to go up t times by storing parent for each vertex. But it will, but it has a time complexity of O of h, where h is the height of the tree, and thus total complexity will be O of q into h, where q is the number of queries, and it will give a TLE. Using binary lifting, we can optimize it in O of q into log of n, where n is the number of vertices, with some pre-computation of n log n. Basically, for each vertex, we will store for each vertex, we will store 2 raised to the power ith ancestor. And why we are doing this? let me just show what we will be storing. Basically, for sixth, we will be storing what is its first ancestor, that is 5. Then what is its second ancestor, that is 4. And what is its fourth ancestor? Let's say it was there was a 0 node 2, which is 0. And we will do this for each of the our vertex in our tree. And using this, now we can find any nth ancestor. Let's say, for example, I have to find 17th ancestor of a given node V. So I can split this 17 as in binary representation as 1, 0, 0, 0, 1. Yes, it can be split like this. So basically, I will just check the 16th ancestor of V, and then of the 16th ancestor of V, I will check its first ancestor. So basically, it can easily be break down into 16 plus 1. And thus, if we store ancestors in the powers of 2 for every vertex, we can check uh, any ancestor of any vertex in log of n. And how we will do this, I will discuss the code later. First, I will explain that why this helps in our code. So basically, say I have a tree 1, 2, 3, 4, 5, 6. Yes. I have this tree and I have to check what is the maximum edge between 5 and 6. So what I can do is, first I will find the least common ancestor of 5, 6, which is 3 in this case. Then my maximum edge would simply be maximum edge between 3, 5 and maximum edge between 3, 6. Why we need to find function? This is because we need to find the unique paths between vertex U and vertex V. For this, first we have to find what is our least common ancestor. Yeah. Simply calculate using LCA log of n and between 3, 6. So our total complexity will be m log n with pre-computation of n log n. And what is our pre-computation? Basically, we'll maintain a 2D array with basically n plus 1 into log of n size, where a j represents two rules of clear. You will have more clarity if you try to implement it yourself. If you have any doubt in this or why we are doing this in order to find the maximum edge between u comma v, you can ask now, or else we will move forward toward the implementation of the question. Okay, from where I have to again explain. I Okay, I will explain from binary lifting again. Yeah. Basically, in binary lifting, for every vertex V, we store 2 to the power ith ancestor, where I goes from 0 to log n. And why we are doing this? Because if we want to now find the 17th ancestor of any given vertex V, I can find the 16th ancestor of that vertex and then find the first ancestor of our new vertex. Because any number can be break down into sum of the powers of 2. And why we are doing this? This is because in our question, it is required to get maximum edge between any two arbitrary chosen vertices u comma v in efficient time, maybe probably log of n. So if we have pre-computed uh, if we have pre-computed the kth ancestor using binary lifting, then we can simply find lowest common ancestor of what is u comma v in log of n. Say it is 3 in this case. Now again using binary lifting, we will find the maximum edge between 3 comma 5 in 3 comma 5 paths and maximum edge between 3 comma 6 paths. So our maximum edge will be simply the maximum of these two. Where 5 are least common ancestor of u comma v. So simply, if I have to find the maximum match between u comma v, I can find it using finding the maximum of u comma a and a comma u paths, where a is the least common ancestor of u comma v. And why we are doing this? We are doing this because we have to check for the unique path between u and v. And the unique path goes from u to lowest common ancestor and v and doesn't crosses this LCA. And talking about the implementation of binary lifting, we can simply maintain a 2D array, say up in this case, where up I comma j represents 2 to the power jth ancestor of our ith index. And the first ancestor is simply the parent for each of our vertex. And for the 2 to the power jth ancestor, say we have to check for 2 to the power 3, which is 8th ancestor, we can simply use our previously computed values of the up, that is 4th ancestor for each vertex. How we can use this? First, we will find the 4th ancestor of I, which is up I2, and then we will again find the 4th ancestor of this vertex, which will be up 2. So we can recompute our values of a matrix easily using these transitions, which is mentioned in this case. So yeah, any doubt in the question or binary lifting or the implementation of binary lifting? I hope the question logic is clear because you can check the implementation later also. But understanding the question first is also important, that why we are calculating LCA and maximum between any two edges. So yeah, if it is clear, then I will move towards my code implementation. I would suggest to implement it yourself also to get more clarity. Yeah, so simply I just first took the input of the edges. This is my input. And this is just the agency matrix. P vector is parent for each vertex. Weights is simply the weight of the edge from vertex V to its parent. And depth, as the name suggests, is the depth of each vertex V. Then I simply construct an MST here using Kruskal's algorithm. And then I run a DFS in order to store 3 things using this DFS. That is, I update P vector using this DFS, the weights, and the depth for each of the vertex. And then simply I maintain the up matrix which I discussed earlier to calculate the LCA, where up I comma j tells us about the to the power jth ancestor of the ith vertex, and max is a similar matrix where max of I comma j tells me the maximum match from vertex I till to the power jth index. index. So yeah, once I have up and max, I can simply iterate for in all the edges. If that edge is contained in my MSG, then simply answer is some of the weights of that MSG tree. But if it is not contained, then first I will calculate the least common ancestor. How that least common ancestor is calculated? First, we will bring both the nodes to the same level. Here, depth of the first node is greater than depth of the second node. So we will bring depth of first node towards the same depth as the second node. And once we do that, we will simply find the vertex which is just below our lowest common ancestor. That is, we will iterate through log of n, from log of n to 0. And if by making that jump, our LCA is not same, we will make that jump. So now we will reach to a place just before LCA, and our LCA will be just above that index. Max W, I have maintained the maximum edge covered in all these travels in max W. So our final maximum W will maximum of this max W I have maintained till now, maximum of T1, 0 and T2, 0. And so my new weight will be my removing maximum weight between edges U, V and the original weight of the edge which I am adding. You can implement it yourself also, as it is a big implementation, and then you will able to understand it better. Is there any doubt in the question solution